This video is just going to revisit the properties of exponents which we covered in class last period. The first property we discussed was the product of powers property. Now we call this product of powers because we're multiplying two things together which have the same base, a and a, raised to some power. Now for this property we need to keep in mind that our bases must be the same. So for our example here, we have base A times base A, so our property applies here. We have base 5 times base 5, so we can apply the property. Again, base 5, base 5, base X, base 3, base 4. No dice on the last problem. We cannot apply this property because these bases are different. So anytime we have the same base, all we're going to do is just add our exponents together. So for the example here, we have 5 to the third power times 5 to the negative 1. So our base stays the same, base 5. We take the third power and we add it to the negative first power. 3 plus negative 1 gives us 5 to the second power, and we can actually evaluate what that is, giving us an answer of 25. So anytime you have a number raised to a power, you can actually evaluate what your answer is. If we're working strictly with variables, you're not going to be able to evaluate what the answer is because we don't know what the variable is. So let's go through these examples quick. Here we have 5 to the second power times 5 to the third power. Bases are the same, we can move on. This gives us 5, which is still our base, to the 2 plus 3 power. 2 plus 3 gives us 5. 5 to the fifth power, and we can actually evaluate this because we're working with strictly integers, and 5 to the fifth power is 3,125. Next one, we have x to the fifth power times x to the negative second power. Now, because our bases are the same, we both have x's. We have x to the fifth plus negative 2. Now, remember, if we have a negative number here, we're going to add that negative number. It's always plus for using product of powers. So 5 plus negative 2 is the same as 5 minus 2, which gives us x to the third power. And that's our final answer. We can't actually evaluate what that is. Now for this last problem here, we have 3 to the second power times 4 to the second power. Now our exponents here are the same, but this property states that our bases must be the same to apply this property. So we cannot do anything with the 3 and the 4 here. This does not equal 3 times 4 to the second power. What we can do is actually evaluate each of these terms separately. So 3 squared is 9, and 4 squared is 16. So we're not applying any actual properties here, but we still can evaluate what this answer is, and this gives us 144. So just keep your eyes peeled for what these bases are, and we cannot apply this property if our bases are different. The next property we addressed was the quotient of powers rule. Now quotient means we are dividing now instead of multiplying, as the product property said last time. So when we're dividing two numbers raised to a power, again with the same base, all we do is keep the same base and we subtract our powers, in this case m and n. So when we start evaluating some numbers here, if we have 6 to the negative third minus 6 to the negative sixth, same base, 6 and 6, we subtract our powers. Negative 3 minus negative 6 equals 6 to the third power equals 216. I think it's a good idea to use parentheses here in both cases, in case we're working with negative exponents, just to keep track of what your signs are when you're adding or subtracting your powers. So in the example here, first one, we have 5 to the fourth power divided by 5 to the second power. Same base, 5 and 5, so we can apply our property. This turns out to be 5 to the 4 minus 2 power, which equals 5 squared, which we can evaluate to be 25. Next example, we have p to the third power divided by p to the fifth power. Same base, p and p, we can apply our property again. P to the 3 minus 5 power equals p to the negative second power. And lastly, here we have 2 to the 4th power divided by 3 to the 6th power. Now we cannot apply our quotient of powers property here because 2 and 3 are different bases. However, as we did in the last example, we can actually evaluate what each of these terms are. 2 to the 4th power is 16, and 3 to the 6th power is 729. So even though we have different bases here, we can evaluate this expression, just not using the quotient of powers property. The next two properties we discussed were the negative exponent property and the zero exponent property. Now, whenever we have some base raised to a negative power here, all we're going to do is get rid of that negative sign, and we're going to put this entire term underneath 1. We're essentially taking the reciprocal of what this term is and just getting rid of the negative power. So for the example here, if we have 7 to the negative 2nd power, just get rid of the negative and make it 1 over 7 squared, which we can evaluate as 1 over 49. So for the examples here, we have 3 to the negative 3rd power, so we get rid of our negative sign and put this entire thing underneath 1. So this would be 1 over 3 to the 3rd power, which again we can evaluate as 1 over 27. And this also works for variable terms here. If we have y to the negative 4th power, we get rid of the negative and put y to the 4th underneath 1. For the zero exponent property, all we said that was any base raised to the 0 power is going to equal the number 1 every single time. Now, in both of these cases, we say that a cannot equal 0. Because in the negative exponent property, we'd be dividing by 0, which we said was undefined. We can't divide anything by 0. The same case here. 0 raised to the 0 power is also an undefined term. So the example, negative 89 to the 0 power equals 1. X to the 0 power equals 1. 25 to the 0 power equals 1. Anything to the 0 power equals 1. Except for 0. The next two properties we discussed were the power of a product property and the power of a power property. Now, think of what power of a product means. We're taking the product of two things, A times B, and we're raising it to some power, M. So we're taking a product and raising it to a power of a product. So and both of these properties are based, can change, but what our exponent's going to do is distribute to every single term inside the parentheses. So the m power hits the a and the b. So ab to the m equals a to the m times b to the m. In the example here, we have 2 times 3 to the 4th power. So the bases are different, 2 times 3, but the 4th power hits the 2 and the 3. So we get 2 to the 4th times 3 to the 4th equals 1,296. Now, we had a discussion in class quickly about why can't you just multiply the 2 times 3 first and then raise it to the 4th power? You can. That's totally okay. That's applying order of operations. However, when we get to variable expressions like this, we can't actually combine what's in the parentheses. So for the examples here, applying the power of a product property, we have 2 times 5 raised to the 2nd power. So the 2 gets the 2nd power and the 5 gets the 2nd power, giving us 2 squared times 5 squared, which equals 4 times 25, which equals 100. Now if we do this the second way, if we multiply the 5 times the 2, we get 10 to the 2nd power, which still equals 100. So as I said before, if we have two numbers inside the parentheses, it's okay to use order of operations to evaluate that term. However, when we have two variables, if we have x times y to the 5th power, we can't do anything inside those parentheses. So the x gets the 5th power, and the y gets the 5th power. And that's as simplified as that term gets. Now, for the power of a power property, we're taking some base and raising it to a power and then raising it to another power. This is like the double power property. So kind of similar to the product of powers. When we take a power and raise it to another power, we're going to multiply the two powers together instead of adding like we did in the product of powers rule. So the example here, 3 cubed to the second power, we're going to take our base 3 and multiply the exponents, 3 times 2, to get us 3 to the 6th, which we can then evaluate to be 729. So in the example here, we just flip-flop the numbers. If we have 3 to the second power raised again to the third power, this looks like 2 times 3 still equals 3 to the 6th, still equals 729. Now, to up the ante a little bit here, we have x squared times y to the 4th, all raised to the third power. Now, the key thing to remember with both of these properties is that every term gets the exponent. So when we have multiple terms in here in the power of product rule, the a and the b both get the m power. In the power of a power property, if we have multiple terms here, like x squared, y to the 4th, all raised to the third power, every term gets the exponent. So the x squared gets raised to the third power, and the y to the 4th gets raised to the third power. So when we evaluate this term, x squared raised to the third power looks like x to the 2 times 3, and y to the 4th raised to the third power looks like y to the 4 times 3. And evaluating those exponents, we get x to the 6th, y to the 12th. So our last property here is the power of a quotient property. So this says that we're taking some quotient, we're dividing some term, a divided by b, and we're raising that to some power m. And again, just like the power of a power property, every term gets the exponent. So the a and the b both get the m power. So for the example here, we have 4/7 squared raised to the second power. So we need to raise 4 to the second power and 7 to the second power. And evaluating that, we get 16 over 49. So let's go through the examples here quick. If we have 1/3 raised to the second power, we simply get 1 to the second power divided by 3 to the second power. 1 squared is 1, and 3 squared is 9. Now when we're working with variables here, if we have x over y to the 5th power, every term gets the exponent. So the x gets the 5th power, and the y gets the 5th power. Now again, when we have multiple terms inside here, we have 2 times x times y all to the third power. Let's say we raise this to the third power. Every term gets the exponent. So when distributing this 3 exponent into the numerator here, we get 2 to the third power times x to the third power times y to the third power, and the denominator 3 also gets raised to the third power. Now, what can we evaluate in this expression? 2 to the third power, we can actually evaluate. That equals 8. X to the third power still just equals x to the third power. Y to the third power still just equals y to the third power. And 3 to the third power equals 27. Now, we should always check here to see if we have any common factors we can pull out. 8 and 27 don't share any common factors, so this is as simple as this expression gets. Let's try an example quick where we can apply multiple properties of exponents. I think a good rule of thumb for working with problems like these, when we have, say, a bunch of expressions inside parentheses raised to another power, just start using order of operations. Work with what's inside your parentheses first, then deal with your exponents, then deal with multiplication or division or addition or subtraction. So, taking a look at this problem here, we have x to the 4th power times y to the negative 2nd power divided by x to the 3rd power times y to the 6th power, all raised to the 3rd power. So if we worry about just what's inside the parentheses here, we have x to the 4th over x to the 3rd times y to the negative 2nd over y to the 6th, all raised to the 3rd power. Now I broke this into 2 pieces here. I have my x powers on one side and my y powers on another side because the only way we can apply our properties of exponents are if we have the same base, x over x, y over y. In this case, this is a quotient of powers problem, so we have the same base, we can apply our property. So x to the fourth over x to the third looks like x to the 4 minus 3. Y to the negative 2 over y to the 6 looks like y to the negative 2 minus 6. And this is all what's inside our parentheses. This is still raised to the third power. So now we can actually do some arithmetic here and get x to the first power, y to the negative 8th power. This is still all raised to the third power. Now, there's two different ways you can approach this problem from this point. You can evaluate y to the negative 8th power, because this is a negative exponent, and apply the negative exponent property, or you can apply the power of a power rule, because we have x to the first power, y to the negative 8th power, both of those raised to the third power. So I'm going to go ahead and just use the power of a power rule here. So we get x to the first times 3 and y to the negative 8 times 3. Remember, each term gets the exponent. X to the first gets the exponent, y to the negative 8th gets the exponent. So we're multiplying 1 times 3 and negative 8 times 3. Now, evaluating what that is, we get x to the third, y to the negative 24th power. Now, in our final answer here, we have y to the negative 24th, so it's really not our final answer because we need to take care of this negative sign. We can apply the negative exponent property, and so we're going to get rid of this negative, and we're going to write 1 over whatever this power is, except without the negative sign. So we get x to the third times 1 over y to the 24th, and this just looks like x to the third over 1, so we can multiply these two fractions together, giving us a final answer of x to the third over y to the 24th. Final answer. So again, when dealing with problems like this, I would say take a look at what you have inside your parentheses first, identify what properties of exponents you can apply, look for similar bases, group all of your similar bases together so they're like terms, and just start chipping away piece by piece.